Okay, now a theorem about local smoothing effects. Okay, in the last video we saw global smoothing effects, now local smoothing effects. Okay, so if n is equal to 1, then we have that the supreme axis of dx 1/2 EIT f of x squared dt is less than equal than c f squared, and if n is greater than or equal than 2, then for all j on n we will have the supreme and now xj in our n of the dxj 1/2 EIT population fx, okay, squared, and now all the dx's, dx1, okay, dxj minus 1, dxj plus 1, and well, dxn dd, okay, this is going to be less than equal than a constant, let's write it here, c f, well, again, 2 squared, okay, and where in this case dxj when half of a function gxt is equal to 2 pi psi j, all of this 1/2 g transform psi t, all of this anti-transform, okay. This is the homogeneous derivative of order 1/2 in the variable xj, okay. Okay, so we're going to prove only for n equal 1. We will leave the case of n greater than or equal than 2. So the x1/2 EIT population f is going to be equal to c, okay, c1/2 e to the minus 4 pi squared it, here is a psi squared, f transform psi, and this has to be all anti-transform, okay. This will be equal to c psi 1/2 e minus 4 pi squared it psi squared again, and now we will divide the f in, let's say, f plus transform psi all anti-transform plus a constant, and again we'll have this part the same, 4 pi squared it psi squared, but now we will have f minus psi anti-transform, where f plus or minus is going to be, well, a characteristic function, okay, or plus minus, well, an f transform psi, okay. Okay, so let's start with dx1/2 EIT and f plus. In the case of f minus is going to be the same. X dt, okay, this is going to be equal to c minus infinity, so let's plug in the definition that we have here, the anti-transform. So this is going to be, we are always in one dimension, psi 1/2 e2 pi ix psi. Then we're going to have e minus 4 pi squared it psi squared, okay, multiplied by f plus. This f plus is of psi, okay. Well, this is squared and this d psi, and has to be also a dt outside, okay. So if we make a change of variables, let's say that 2, I'm going to write here 2p psi squared is equal to r, we will obtain c, well, the two um, uh, integrals are 1 over 4, and consider also that psi is going to be equal to square root of r 2 pi. Okay, taking into account that, then we will have that e minus 2 pi I t r e I x square root 2 pi r af plus. Now this f is going to depend on the square root of r over 2 pi. Okay, dr r1/2 squared dt. Okay. Okay, so notice that we can get rid of the integral in dt, and we can cancel this r1/2 r1/4 1 over 4, and we can obtain integral eix 2 pi r f transform r over 2 pi 1 over r1/4 or 1 over 4 and squared dr. Okay, and recall that this is psi. Okay, this is psi. Well, this actually is not psi. It's 2 pi psi, and okay, so this will be equal to c times, well, the integral infinity of f transform plus psi squared. Okay, and using Planck-Herold's theorem, I have that this is f plus squared norm 2. Okay, so proving this for f plus, we obtain the inequality I wanted to see. Okay, well, now a corollary integral from minus infinity to infinity, and now integral of absolute value of x less than equal than r, okay, of dx 1/2 e I t Laplacian f squared dx dt 1/2 is going to be less than equal than c r 1/2 norm f 2. Okay, where dx 1/2 once again is going to be, let's say, of bxt 2 pi psi 1/2 b transform psi t anti-transform. Okay, from this corollary and some other properties that we already saw, then if f is in L2, always in Rn, then EIT Laplacian f is going to be an L2 log, and so using this we will have that EIT f is going to be an H1 half log. Okay, we're improving a little bit for the half x. This is for almost every t real number. Okay, so another thing one can prove is that in the case that n is equal to 1, so the norm dx 1 half minus infinity infinity EIT Laplacian f t dt norm 2 is less than equal than c infinity of norm of f. I'm sorry, this has to be, now the variable has to be x, k, and this is 2 dx. Okay, and you can have the same the corresponding inequality for n greater than equal than 2. Okay, so now we're going to take into account the inhomogeneous problem dtu I Laplacian u plus an f xt u x0 is u naught. Well, in this case, let's say 0. Okay, mixing our n, and the t is a real number. Okay, so now for this problem, we're going to have the following theorem for the solutions of this. Okay, so if uxt is solution of what we saw, the inhomogeneous case, then it satisfies the supreme x minus infinity infinity dx uxt squared dt 1 half c is less than equal than c minus infinity infinity integral minus infinity infinity f xt squared dt is 1 half dx. Okay, and this is the case for n equal to 1. In the case on n greater than 2 or equal, then we will have for xj rn dx j uxt squared 1 half less than equal than c minus infinity infinity rn fxt squared d mu j dt 1 half. This has to all be multiplied by dx j, where d mu j is equal to, well, dx1 dxj minus 1 dxj plus 1 dxm. Okay, so these are some theorems concerning the smoothing effects for the group EIT Laplacian minus infinity infinity. Okay.